So, what is calculus good for anyway? What's it used for? When I was in high school in calculus class, my dad would ask me these questions, and I was having difficulty with it, and I really wasn't able to explain to him exactly what it was for. I would try to use examples. Well, if you're going to space in a rocket, and your rocket's getting lighter, but your thrust is the same, your acceleration's increasing, and he couldn't grasp what it would be good for, and I couldn't explain it. But here's an application. Let's say we have a mass that is 2 kilograms. Now, it turns out we don't have to know that right now, but we've got a mass that's 2 kilograms. And normally, when we plot data on a graph, we are using time as the independent variable on the x-axis. But we don't have to do that. It could be another attribute other than time. And I'm going to use a different one. In these cases, I will use velocity as the independent variable. I want to show that the faster a car is going, the more kinetic energy it has that has to be removed by braking. And so how do you get kinetic energy? Well, kinetic energy is 1/2 mass times velocity squared. And what happens when we plot the kinetic energy of an object based on its velocity at that time? We aren't going to do any calculations with acceleration, velocity, or displacement like we usually do in the books. So notice if we're looking at velocity on this axis, which is kind of strange, kinetic energy this way, you get this graph. And what got me thinking about this was when I was in school, my dad always had us downshift in the standard shift vehicles to slow down so we weren't wearing out brake pads. It wasn't all that non-counterproductive. It was kind of counterproductive. But anyway, and one time I was downshifting and I got all the way down to 3rd gear and let it get down there idle, and then I shifted to neutral. I was like, well, why didn't you go ahead and shift down into 2nd? Well, I couldn't quite explain it at the time, but if you look at the energy that is lost, I'll get to the text here in a little bit, that if you're slowing from, let's say, 5 meters per second down to 4 meters per second, or 25 down to 20, you'll get a bigger drop in kinetic energy when you're moving faster. Once you get slowed down to 2 meters per second down to 1 meters per second, that drop in energy is less. So in my mind, and I wasn't able to explain this to him, but downshifting down to 3rd and then just coasting the rest of the way and applying the brakes wasn't really using much brakes. There wasn't much going on down here in terms of energy loss. All the energy loss was at the higher speeds and in the higher gears. So if you're driving a standard shift car, and these numbers don't work for a standard shift car because the energies aren't that big and the speeds aren't that big, this would be more like a cart. But anyway, if you're driving a standard shift car and you're slowing down by downshifting, most of the braking work is done at the higher speeds. At the slower speeds, less work needs to be done on the brakes. In this graph, 9 joules of energy are removed here when slowing from 5 to 4. Just over this time interval. From 5 to 4, you're going to lower your kinetic energy by 9. But when you're slowing from 2 to 1, you're only lowering your kinetic energy by 3 joules from 4 to 1. So I was right. You downshift to 3rd gear and coast up and catch the rest of it on the brakes. This got me to thinking. I was realizing this last spring on the way home on a sunny day when I was downshifting down into a stop sign as to how could I explain that to him? Aha! So I was thinking about it. The key is to make the graph a velocity kinetic energy graph, because that's what I really want to study. I want to study the effective speed on kinetic energy. And when I did that, I realized some things. If I could take that graph with respect to velocity and get those meanings out of it, what would the slope be? And what would the derivative be? Well, if you find the slopes along there, which are your derivatives, you would be finding the derivative of the kinetic energy, derivative KE, with respect to the change in kinetic energy with respect to change in velocity. is equal to the limit as the change in velocity, which is this little delta v, getting closer and closer together. As that interval of velocity gets smaller and smaller near zero, of the kinetic energy, 1/2 mv squared, you take the derivative of that and you get mv. And that was a light bulb going off. That is momentum. And so that slope there, and that slope there, and that slope there, and that slope there, and that slope there, they're all momentum. And so are all the other slopes all there everywhere else in between. And if you plot them, you would get plot points that came out on a straight line. Oh, that was a revelation. So velocity is speed in a given direction, but what is momentum? Well, momentum is mass times velocity, or we use the symbol p for whatever reason, equals m times v. Now, I didn't put the vector arrow symbols in here, mainly because I didn't want us to have to think about it when we were doing the calculus. So you can think about this all being a straight line and put those arrow vectors in your own mind's eye if you want. So when we plot that momentum, we get a graph that is a straight line. That's using these slopes here. The slope's bigger and bigger and bigger and bigger. So the lines go at a higher, or the dots go at higher and higher and higher numbers. Well, then what do you do with that? If we plot that data, we get that graph, but what's the slope of that mean? Well, that slope is a derivative, and it is the mass of whatever object we've got. Now, that's weird, but it's true. So if we find the derivative of the momentum, basically your delta momentum over delta v, you get the limit as your velocity increment approaches zero and gets smaller and smaller of m times v. Take the derivative of that, you get m, which is mass. And as you plot that data for this slope, this slope, this slope, this slope, and this slope, you get the same slope every time. So you get the same mass every time, which is 2, 2, 2, 2, 2, which is fortunate because your mass of this does not change. So the mass is 2 kilograms. And that stays constant through the increasing or decreasing velocity. And it says as long as you're not going too fast. In other words, as long as you're not near the speed of light, this works. And if you, okay, now what? So if you can do that with derivatives, what can you do with integrals? Kind of the reverse process. So if you take the integral of this mass with respect to velocity, you should get momentum. And if you take the integral of momentum with respect to velocity, you get kinetic energy. So if I find the area here, and then here, and then here, and then here, and then here, and I plot all those, the area under the curve would give you the momentum. Area is length times width for each one of these little rectangles, or any combination of them, or all of them. You get momentum. And so the area is the integral, in this case, from 0 to 5 of mdv. And so you work it out like that. So when you come up with, the equation for momentum when you take the integral of this. The integral of m with respect to v is mv. That's momentum. And when you plot that data for this area, and then this area, and then this area, and then this area, and then the whole thing, you get this point, and then this point, then this point, then this point, then this point. You get the momentum velocity graph. And if you take the area under this momentum velocity graph, you take this area, and then this one, and then this one, and then this one, and then this one, you'll get the data points for here, 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 and there. Then let's back up. If you work this, areas, they're all triangles, and the area is 1/2 base times height, or 1/2 momentum times v. That'll get you the answer, or whatever combination of answers you want from your triangles down here. Or we could integrate that. And we didn't have to integrate it because everything's linear so far, but if this wasn't a straight line, if it was some sort of a curved function, you'd have to integrate it. So from 0 to 5 of mv dv, well, when you take the integral of that, you end up 1/2 mv squared, which is kinetic energy, all over again. So you won't find this, probably, I've never seen it in any textbook, but it's a really good, interesting idea of integrals and derivatives. A really good application of integrals and derivatives. So kinetic energy is the integral of momentum, and momentum is the integral of mass. And they are one another's derivatives also. So, interesting lesson. Take that with you because you won't read it in your book.